Let's start to explore vertex form. So we looked at standard form already. We saw y equals ax squared plus bx plus c, right, where we had a fully distributed trinomial. Vertex form, as we can see up at the top here, we have a perfect square. So we have x minus p and then that whole binomial squared. That means there's still an x squared value. It's still a degree 2 polynomial. We just have a bit of some factors inside and then some leftovers outside. So we're going to look at what do a, p, and q do. So we have a few functions here to talk about a. We have x squared, we have 2x squared, and we have 1/2 x squared. So all I'm doing is I'm changing the coefficient. I'm not worried about adding or subtracting anything to x yet, or adding or subtracting any constants on the outside. I'm going to pull up Desmos, which is a graphing online app. You can see at the top desmos.com/calculator. And let's look at each of these graphs. So let's look at x squared. Well, we've seen x squared before, right? It's that basic parabola. My vertex is at 0, 0. I open up. I have points at -1, -1, right? -2, +4, and so on and so forth. If I change my a value, so let's draw another graph now, where I have 1/2 as my coefficient. Notice that in comparison, my graph has gotten wider. I still have a vertex at 0, 0. But now, when I go over when x is 1, y is only 0.5. And then when x is 2, y is now only 2 instead of 4. So notice that as we keep going, right, it's like we've pushed this graph down from the top. We've pulled out the sides a little bit. So when I have an a value that's a fraction, I'm going to notice my graph gets wider. And if I look at something like 2x squared, notice that this green graph is narrower than my original red graph. Again, it still has a vertex at the same place. They all meet in the same location. But now when I go over 1, I've already gone up 2. So it's growing twice as quickly as that red graph. So that a value is what we call our vertical stretch factor. Imagine if you had an elastic band, right, and you nailed it down here so it can't move, but you start pulling it vertically. So you pull it up from the top, right? If I'm pulling it 2 times as tight, right, with this coefficient of 2, the graph is going to get skinnier because I'm pulling it harder. I'm pulling it further. And if I pull half as hard, right, this blue graph compared to the red, it's almost like I'm pushing down, right? The sides are going to start to bow out. That's what our a value does. Our a value is what we call our vertical stretch factor. And we talked a bit about this in our standard form because it also had an a. Vertical stretch. So if a is greater than 1, if we're pulling harder, right, if our a value is 2 or 3 or 4 or anything bigger than 1, then we find, and I'm going to be brief with my words here, that our graph gets a lot more narrow, right, because it's stretched further. And then if a is between 0 and 1, right, if a is like 1/2 or 1/3 or 1/8, then our graph is going to be wider. Notice that I'm not talking about anything below 0 because we already know what happens when a is negative. When a is negative, and we'll look at a quick example here. When a is negative, it doesn't matter what the number in front is. We just know that it's going to open down, right? Notice that the purple graph is just as wide as the green graph. It's just opening down. And notice that the black graph is just as wide as the blue graph, but it's just opening down. So that's what our a value does. What happens when I start to add some values outside, when I add some q values? And this kind of looks like c, but we'll see how it can be a bit different. So let's clear these graphs out of here. We'll keep our regular x squared. Right, that's our basic graph, what we like to compare to. We're going to say what happens when, after the squared on the outside, I add 2. Let's change the color just so we can compare this. Well, my graph, and it's kind of hard to tell, but my graph is just as wide. All I've done is I've moved it up. And if I notice by my vertex, I've actually moved it up 2 points. What happens if I subtract some value? And notice here again, it's just as wide, but I've moved it down 3 points. I could even look at something like x squared minus or plus b. Right, and this is one of the beauty of Desmos. And we can see, right, if b is 1, I've moved up 1. If I move b to a negative, right, it's taking that graph. It's not actually, it's kind of an optical illusion. It'll help if I zoom out a bit. It's not actually getting any wider. It's just moving where the bottom of my graph is. Or if I'm going up into the positives, it's moving where the top of my graph is. Right, it's moving us up and down. So Q, the way we describe this, right, it says it slides the parabola. We're going to say vertically. Right, because Q moves us up and down. Q affects our Y values. Notice that everything stayed right in the middle. So we have one last variable, our P value. Notice this one's inside the brackets. That's what makes this different from standard form. Let's see what our P value does. So again, let's get rid of some of these graphs. Let's look at x minus 2 squared. And so notice now my graph hasn't moved up or down compared to the red one, but it has moved 2 units to the right. Let me zoom back in so we can see. Which is funny because it actually says minus 2 here. So what happens when it's positive? What happens if I put x plus 3? Well, now this is going to move 3 units to the left. So the thing with P, if we go back and we look at our equation, I'm going to go back to the first slide here. Notice that it was already x minus p. The equation already had a negative worked into it. So P slides our parabola horizontally. But by a factor of negative, whatever we're dealing with. We need to worry about switching the sign. Right, x minus 2 actually moves us 2 to the right. And in this case, our p value is actually positive 2. Because remember, p was whatever followed the negative sign. We had x minus p. P is just the number after the subtraction. So in this second one, p is positive 2. In this third one, remember we said p follows the subtraction sign. Well, we don't have a subtraction sign here. But what if I wrote this as x minus negative 3 squared? Right, that's the same thing. And we can see now that I'm actually subtracting a negative 3. So, in summary, in vertex form, P tells us how much we move left and right. Right, it's the horizontal translation. Q tells us how much we move up and down. It's the vertical translation. That means that PQ, the point PQ, is going to be our vertex. Because it's essentially asking us how far have we moved it from that original vertex of 0, 0. We'll take a quick look at that. Let's go y equals x minus 2 squared plus 5. Notice that our vertex is at 2, coming from the p value for x, and 5 coming from the q value for y. And again, if I wanted to do a general case here, I can move P and Q around, right? P moves us left and right. Q moves us up and down. And if I move both, it's telling me where my vertex is, right? P is 2.8, Q is negative 4.1. Notice that's where my vertex ends up because I'm moving it from that original point of 0, 0. It also tells us a few more things. X equals P is going to be the equation of our axis of symmetry. Again, that's because that axis of symmetry always runs right through the middle. So whatever that P value is, it does two jobs. It tells us the X coordinate in our vertex, and it tells us where our axis of symmetry is. Q is also going to do two jobs because it's going to tell us the Y coordinate of the vertex. But remember that vertex is either our maximum or our minimum point, and that's dependent on the Y value. It's asking us what's the highest Y value our graph reaches or the lowest Y value. So Q does double duty as well. Q is also the max or the min value. And A, the reason it's still called A is because A does the same thing it did in standard form. A tells us which way it opens. Positive A opens up and negative A opens down. And it also tells us how wide our graph is, right? Wide or narrow. So the first step is being able to recognize, being able to pull A, P, and Q out of an equation. So let's look at these functions here. So let's look at this first one. We have 2 times x minus 1 all squared plus 4. A is that value out front of our bracket, right? The coefficient. And so in this case, A is positive 2. B is the value after the subtraction sign, keeping in mind that, again, that negative sign is part of the equation. We're saying what follows. If it helps, you can think about just switching the sign. If it says x minus 1, then P is a positive 1. And then Q is that value on the end as the constant term that's being added outside the brackets. Q doesn't do any weird switching or anything. So here Q is positive 4. And we're going to use these ideas to find the vertex. So let's look at this first one. Again, reminder that our vertex is P and Q. So this means that our vertex is at 1, 4. We can also find out more information, right? Because this opens up, we know that Q would be a minimum. So we would have a minimum value of 4. Because we know that the axis of symmetry runs through the middle, we know that the axis of symmetry would be x equals 1, right? Those come from our P and Q values, and with a little help from A. Let's look at the next one. Negative 3 x minus 2 squared minus 4. A is that coefficient out front. So A is negative 3. Again, we keep any signs we see. P is the number after the subtraction sign. So again, if it says minus 2, we want to be extra careful with P. P is positive 2. And then Q, we're subtracting 4 outside, so we keep that negative sign. Oops. Q is negative 4. So again, the vertex for this would be at 2, negative 4, and we know that it would open down because of that A value. In the last one, A, well, A is our coefficient out front. If I don't have a coefficient, remember, anything can be multiplied by 1. Everything has an invisible coefficient of 1 if we don't see anything there. That just means that it hasn't been stretched at all from our original graph. P is the number following the subtraction sign, so we want to be extra careful here. A plus 4 is actually a minus negative 4. Right? Or again, that idea that we switch the signs. So P is actually negative 4 in this case. And Q plus 3 on the end. So Q is positive 3. So our vertex here is negative 4, positive 3. And this graph opens up as well. So let's try to sketch a graph. Say we're given a function. Vertex form is ideal for sketching. Whenever we were sketching in standard form, we had to be plugging values into our graphing calculator. Vertex form tells us a lot of those main points already, so that we can sketch this much easier. The first step is always pulling out your A, P, and Q though. So just like we did on the last one, A, that coefficient out front, we don't see anything there, so it's a 1. P, we flip the sign on the inside, it's going to be a positive 2. Q, we take the constant, it's a negative 3. So as we think about this, direction of opening, right, that comes straight from our A value. Because our A is positive, this graph opens up. Our vertex, in the past we had to use our calculator, but because we're in vertex form, we can pull it right from our P and Q values. So our vertex is 2 and negative 3. Let me clean that up. Right, again, that's coming straight from our P value is our X coordinate. Our Q value is our Y coordinate. We can continue on that theme with our axis of symmetry. Right, remember it runs right through the middle of our graph, so it's also going to be our P value. We said X equals P. So notice that 2 shows up in 3 separate places. Our y-intercept, we actually have to find this a little bit differently now. That's the one downside. Standard form was great. Standard form had that C value that told us the y-intercept. Vertex form, while it tells us the vertex, it no longer tells us the y-intercept. But we know a thing or two. Let's find this one algebraically. We know that a y-intercept has an x value of 0. That's what puts it on the y-axis, the fact that it hasn't moved left or right. And we have an equation. We know that our y values come from taking our x values, subtracting 2 and squaring it, and then subtracting 3. This is just from the equation up top. Right, f of x and y are interchangeable here. But let's plug in that value of x we know. Right, up top, that's our general equation. That's going to tell us about all the x's and y's on this graph. If I'm giving you a specific x and we solve this equation, it's going to tell us the specific y at that point. So we just make sure we follow our correct order of operations. I deal with operations inside the brackets first, so I do 0 minus 2. Then I have to deal with exponents, right, making sure we're going through bed mass, right, that correct order of operations. I did brackets. Now I'm going to do exponents. Negative 2 squared, be careful, is positive 4. If you're plugging this into a calculator, or specifically a graphing calculator, make sure you use brackets. Because your calculator is also going to try to follow order of operations, but what it's seeing is it says, okay, exponents first, 2 to the power of 2. And then it's saying, okay, next is multiplication. Now I'm going to multiply by, it treats this negative sign as a negative 1. So unless you put those brackets around, it's going to get confused and give you the wrong answer, right? This is not correct. Negative 2 squared is negative 2 times negative 2. We should get a positive result. So we get 4 minus 3. Last thing is to do our subtraction. And y equals 1. So that tells us that we have a corresponding point at 0, 1, which, because we chose that x value of 0, that's our y-intercept. So I can plot these points, 0, 1, 2, negative 3, right? And we know this graph is symmetric. We know that it's going to open up on both sides. So if 2 points to the left, I'm up 4. 2 points to the right, I'm also going to be up 4. All right, everything has to be reflected around this vertex. And I can just try my best to connect those points. So there's your graph sketched without a calculator. I want you to try the rest of these examples, and we'll move on to going in the opposite direction after this.